Hello everyone, welcome back to the latest lecture session. We are more or less at the end of our course, right? I think we have 3 or 4 more sessions to go. Obviously, we are talking about the sludge that is coming in as we look at various kinds of treatment, as in from primary treatment you have sludge, secondary treatment you have sludge, and we are looking at how to manage it, right? Let us look at the ways. Residual management. So, first one is thickening. What is it that I am trying to do? Increase the solids concentration. Why? Because that will lead to reduced size requirement for the later treatment systems. Yes. And how do we achieve that? Typically by gravity, and depending upon the type of sludge, dissolved air flotation or gravity belt, right? And then stabilization, as in my secondary treatment unit sludge is biomass, right? It is active or it is cell. So, again that will decay if we do not stabilize it. So, that is what we are trying to do here, right. Decrease the biodegradability, meaning the putrescibility of organic solids. In the meantime or in the process, we want to kill any pathogens that we have in the sludge, right. Obviously, if it is inorganic sludge from primary treatment during water treatment or such, or if it is grit and such, obviously we are not going to look at that, right. Specifically for organic what do we say, sludges. Yes. So, conditioning, improve dewaterability of solids. Later I want to dewater this solid. Why is it? Well, I want to decrease the volume that I am going to handle, and rather than sludge I want to handle solids which are easier to handle. So, to do that I am going to condition it, right, improve dewaterability of the solids. Yes. How do I do that? Typically by adding the relevant what do we say, cations or such, let us say, right, different polymers. So, then the final step is dewatering, increase solids concentration, so that as I mentioned we will handle it as a solid rather than as a sludge, and disposal to landfill or apply it to soil and such. Yes, we will move through this. Let us look at the bigger picture here. So, depending upon the kind of solids coming in, some preliminary options, blending or grinding, and then for thickening, right, increase the solids concentration. You see that we have different kinds. Typically we have gravity, flotation, right, and gravity belt, right. These days people are also looking at rotary drum or belt press and such. And after thickening, right, we now have greater solids concentration. Depending upon the type of solids that you have, you are going to have stabilization, as in anaerobic or aerobic digestion. Lime stabilization too is required, that is with respect to pH, we will look at that later. Then conditioning, typically you add chemicals so that the dewaterability is relatively better. So, dewatering, right. So, what do you see here? We see different kinds of dewatering equipment, as I mentioned, belt filter press, which is also sometimes used during thickening itself or at the stage of thickening itself, and inclined screw press, yes, filter press, yes, these are the different ways. So, then some thermal process if required, and then land application. This is the whole cycle. Let us move on and look at where we are here, right. So, the first step would be thickening. So, before I move on to thickening, I just want to give an idea about what is it that I am trying to do. As in, if I say do something, I need to be clear, as in what are the specific objectives at the end of the day. Maybe in the Indian context we do not have them what do we say, spelled out clearly, but many countries have them spelled out clearly. So, I am trying to decrease the concentration of the pathogens in the relevant sludge. There are other aspects too, as I mentioned, putrescibility or the biodegradability that we want to decrease, but major concerns are with respect to pathogens, right, fecal coliform and salmonella. And how do I achieve that? Aerobic, 40-day solids retention time at a particular temperature or 60-day solids retention time at a particular temperature, air drying, anaerobic digestion, composting, right. These are different stabilization methods, but we will look at these later, but I wanted to mention them here, right. When we are talking about pathogens removal, when we look at stabilization, we are more or less taking care of the pathogens. And another aspect to be concerned about though is the metal contaminants. Depending upon the kind of sludge, let us say if it has what do we say, a lot of or not lot, high enough metal concentration, you do not want to take that sludge and apply that to a land or agriculture land, right. It has to probably go to a landfill. So, you will also need to be concerned about or be aware of the metal contaminants, the usual ones are listed here, right. That is something to keep in mind. Let us move on. So, residual treatment, we are talking about thickening now, right. Thickening, we want to increase the solids concentration. As I mentioned, gravity one is the most usual and simpler one. Let us move on. Okay. So, in thickening, right, think of it, or think of our secondary settling tank, right. There too you see some what do we say, how can I say this, yes, some level of thickening there, right, or even in the sludge, once you collect it and by gravity you are going to see thickening. There are different stages here. Upper stages typically type 1 and type 2, but most of the relevant depth you are going to see type 3 and type 4 settling. Type 3 zone settling, right, where you have a clear, what do we say, interface between solids at low concentration or water that is relatively clear at the top, and below solids at high concentration. And then much further down you are going to see compression settling. Obviously, we discussed this earlier, we are not going to look at that in detail here. So, type 3 or zone settling, right, like the thickening function of activated sludge secondary settler. We discussed this in that context, you can go back and look at those aspects, right. And much further down you will also have type 4 or the compression settling. So, we are trying to increase the solids concentration, and we looked at these aspects, right. As I mentioned, most widely used is gravity sedimentation, sometimes dissolved air flotation, especially depending upon the type of sludge that you have. If you have sludge or the flocks are such that they are relatively more buoyant, then rather than trying to settle them down, you will inverse the process, you will introduce air under pressure, so that these buoyant sludge particles or solids will move up to the surface where they will be removed. In gravity settling, what is it that I am trying to do, or sedimentation, pardon me, I am trying to see to it that, let us say this is the interface, this is moving down, right. Here I have relatively clear water with less solid concentration, here the solid concentration is relatively high. This is what I am doing. In dissolved air flotation, let us say I am introducing air under pressure, right, and bubbles are formed, they will go up, and along with it they will take some of the buoyant solids, and at the top you can remove the solids. So, you can see it is an inverse of the gravity sedimentation in a way. Let us move on. Gravity belt too, yes, especially for primary sludge from water treatment plants. Okay. So, flotation and gravity thickening. So, this is best with primary sludge, yes, it increases the solids concentration from 1 to 2% to 10% or 3% to 10%. Flotation, it is as effective with respect to activated sludge thickening. Why is that? Here the activated sludge is flocks, right, and flocks we have filamentous some, and again flock forming bacteria. Again note that the cells itself have a lot of water, and also there is a lot of water entrapped within the relevant flocks itself. Yes, you have flocks coming together, one is water inside the cell of the microbes and even water trapped between the flocks. So, in those cases, especially when you have, what do we say, sludge or particles that are relatively more buoyant or solids which are relatively more buoyant, you will use dissolved air flotation, and we can concentrate it to 3 to 6%, right. Again, primary sludge typically gravity thickening, and secondary sludge flotation, let us say, and then for further processing later on as in stabilization or such as required. So, gravity sludge thickening, so it has two zones. The first one, upper zone, is the clarification zone, the one below it is the thickening zone, right. So, here as I mentioned earlier, we are going to witness type 1 and type 2 as in where we have relatively discrete, what do we say, settling, relatively again I guess, right, individual particles settle. Thickening zone where we have increase in concentration, and typically we see the zone settling, and much further down you can maybe see the compression settling, let us say, right. These are the aspects to be looking at. Let us look at the figure if I have it. Okay. So, as I mentioned, pretty commonly used is gravity sludge thickener, and you want to break up the gently break up the relevant sludge. So, you have going to have pickets that rake the sludge, we will come back to that. Why is it? We want to break up the sludge, right, so that it can release the water, that is the key issue. Why do we have them? To break up the sludge. Why do we want to break it up? It is easier to release the water. So, primary sludge can be thickened from 4 to 8%, activated sludge 1 to 3%, even that is considerable, let us say, right. And obviously, I guess I have a figure, this is easier to look at, yes. So, here I have influent or flocculent suspension, yes, and here I have the top of the sludge blanket where we can see the zone settling, and then maybe the type 4 settling at the bottom here, let us say, right. So, here we have the supernatant, which is clarified effluent. So, here there are two aspects to note. Here, because of the zone settling, right, there is one kind of flux. The term I am using is flux. Flux here is mass of the solids or such per area per time, right, or through a particular cross sectional area, which is this, let us say, how much mass is going through per time. And as you know, I mean steady state, yes, but in general if I take a batch system, you know that it is going to decrease here, right, it is going to come down. As in initially my interface is here, after some time the interface comes down and maybe further down here, let us say, right. So, there is a velocity with which this interface comes down, let us say, right. So, that itself will lead to a certain flux, right, mass per area per time. And what is the other flux that is going to be relevant here? So, the sludge that is going to be collected at the bottom, you are not going to let it accumulate all the time, right. What are you going to do? You are going to take it out, yes. For example, if it was the secondary treatment system, as in for the wastewater, we know that we have the aeration here, right, where we give oxygen, and here we let it settle down, right. Here it is not entirely sludge, I guess, right. So, what are we doing here? Even there you are going to have type 3 settling, yes, but this sludge, what are you doing? You are not wasting everything, you are recycling it here, right. So, again we are going to have an underflow because you are removing the flow from the bottom or the solids from the bottom. Similarly, here also you will remove the solids from the bottom, the ones that have been, or the solid or the sludge that has relatively thickened, you are going to remove it, right. It is similar to what we are doing in the secondary settling tank. So, again the sludge is going to be removed. So, there are two fluxes, one because of the zone settling and the one because of the underflow, right, one because of the underflow. That is something to keep in mind, yes. Let us move on and look at what we have. So, to be able to get that, you sometimes need to conduct batch tests. This is what I was mentioning earlier, right. So, here I guess you have different batches, yes, and you can see that, you know, the zone settling, I guess you can see this particular interface coming down with time, let us see, right, and it is gentle mixing and batch. So, the zone or zone 3, right, or type 3 settling, there is a velocity with which this interface is going to come down, and that velocity you can plot for different concentrations here, okay. Why is that relevant and such? We will look at it. What do we have? We have time and we have solid to liquid interface depth, as in this depth, right, and you can plot that for different concentrations. So, as I mentioned, the solid flux, right, solid flux is mass per area per time, right, mass per area per time. So, what is it equal to? It is going to be equal to the velocity, this velocity that you are measuring, into the concentration of the sludge, right. As in velocity units are dimension, or dimension I am saying L per time, yes, and what do we have here? This is the concentration, right. So, if I have mass, let us say mass per, what is it, mass per volume, right, liter cube. So, L, it becomes L square. So, mass per area dimension square per time, right. So, that is what we have, velocity of that particular interface into x, right, the concentration of that particular sludge. That is something to keep in mind. So, design of thickening basin, two aspects to understand here. There are two fluxes, as I mentioned, one due to the underflow and the other one due to the zone settling, let us say, right, zone settling. So, in this context we have two fluxes, right, let me call that G1 and G2, we will look at the relevant aspects later, yes. So, understand this, I am putting in sludge at a particular rate into the relevant thickening tank, right, or gravity thickener, and I am removing it underflow at a certain rate, yes. but also this thickening is occurring due to type 3 at a particular rate. So, you have two fluxes. So, if the rate at which I am putting it in is greater than this overall flux or the total flux, the limiting flux, we will look at that later. What is going to happen? This interface which has been at steady state, or which at steady state you want it to be 1 meter above the relevant bottom, it is going to increase. And if I am still putting in a lot more than I can remove, or than I am removing, what is going to happen? It can even lead to overflow and your effluent will not be clear. So, that is something to keep in mind, and that is why we need to design for the thickening basin, right. Let us move on. So, we can obtain the zone settling velocity, right. You looked at the graphs and such, you know how to do that, the previous one, and you are going to plot G, right, and from that you will choose the Cu, let us say, right, or Qu by A. We will look at the relevant graph and use the graph to obtain the limiting flux, and from that you can get the relevant cross sectional area, let us say, right. For example, once I get the limiting flux, G limiting, right, and I know the mass loading rate, or the rate at which the solids are coming in, mass per time, let us say, right. So, I have let us say mass loading rate, let us say, right, mass per time, let us say, right, and I have the limiting flux, which is mass per area per time. So, from this, as you can see, if I divide the loading rate by the flux, I am going to get the cross sectional area that is required, right. So, from this cross sectional area, if it is circular, I can get the diameter and then check for that particular diameter, and then I will also have to calculate the overflow rate and see if the overflow rate is acceptable or not. Again, that is one way to go about it, right. Let us move on and see how we can get this limiting flux. Again, solids and concentration in the underflow. Okay. So, here we see two aspects, right. First, let us understand the figure. We have solids flux here, solid flux, and here we have solid concentration, right. Note that if this is the graph, and now I am talking about this gravity flux, the one due to gravity or due to the zone settling, let us see, right. So, at low concentration, more or less it is going to be equal to the flux, let us say, concentration into this particular velocity, which term are they using? V. C into V is going to be proportional to the concentration when the concentration is low. Why is that? Because when the concentration is low, it is more or less like, the particles are not coming in, what do we say, are not being affected by one another when they are settling down. So, it is more or less like discrete settling. So, again there you are going to have, what do we say, relatively low velocities of settling of that particular interface, let us say, and then you are going to reach an optimum where you are going to have optimum for the due to the zone settling, and then again it is going to decrease because then you are going to have compression settling and such, right. So, I guess that is what you see here, the gravity flux first when at low concentrations it is like discrete settling initially only, and then at relatively higher concentrations you are going to see the zone settling or the type 3 settling, and that is when you have the peak, and then you are going to have hindered settling if you keep increasing the concentration, right, and that is what you are going to see. I guess I should have drawn it like this, yes, and then hindered settling. So, this is the peak that you are going to have, but again as we know that in the treatment gravity thickener, one is the flux due to the zone settling, the other one is because you are also removing the sludge due to the underflow, right. There is a flow here. So, that is the underflow flux, right, and that is what we have here, underflow flux. So, there are two fluxes as I mentioned earlier, one is due to the gravity flux and other is due to the underflow flux, let us see, right. So, the total flux as you can see is this green one, and this here is the limiting flux. In the operational range, this one will be the limiting flux, yes, this is the limiting flux, and this is how you can get it from the relevant graph, and at that the concentration is called Cl, right. So, that is something to keep in mind, Cl, yes. So, this is the relevant aspect. So, if we look at it at this particular point or this particular concentration, what do we see? There are two aspects of the total flux, one is due to the underflow, that is what we have here, the other one is due to this particular gravity flux, which is this particular part, I guess, Yes, so that is something to keep in mind. So, the total flux will be 1 due to the underflow, 1 due to the gravity flux. So, that is something to keep in mind, and from this figure at this particular point you will have the limiting flux, right. So, let us move on. Design of thickening zone. As I mentioned, we will have the batch flux analysis, right, and this again will be equal to Cs into the zone settling velocity. Yes, where Cs is the concentration of the suspended solids concentration and V here is the underflow velocity, let us see. So, one aspect to note, sludge withdrawal rate, right, Qu is the sludge withdrawal rate, which is the underflow. Qu, right, it is going to be velocity times cross sectional area. So, thus velocity, how do I get that? It is obviously equal to Qu by A, right. Why am I looking at this? Because as you know, in the total flux I have two aspects. One is concentration into the velocity of that particular gravity flux interface, and the other one is concentration into the downward velocity due to the sludge withdrawal. So, this one too I need that, right. So, now do I get that? I get it from relevant what do we say, tank surface area and sludge withdrawal. So, that is this second term here when we are calculating the total flux, right. So, total flux G is equal to C into V, flux due to gravity settling, and C into U is flux due to the bulk fluid motion due to the underflow which I am withdrawing, right. And typically the minimum total flux or minimum in total flux is the steady state operating point or critical flux. There earlier we saw this particular kind of graph, right. So, this is the critical flux, right. So, G critical, let us say, or limiting, and at this point you are going to have this critical solids concentration, right. This is what we are talking about, critical flux and critical solids in the previous one, right. So, that is something to note. So, in general you would want to maintain your steady state. Once you start operating your gravity thickener, you are going to maintain it at steady state or try to. So, in that context you have to maintain it around GL, let us see, right, this limiting one at steady state. And if I add much more, right, what is going to happen, and if I add much lesser to the tank, what is going to happen, we will look at that. Okay, before I go further, how is the sludge coming in, right, or how is it coming in? So, here I have the tank, Q plus Qn or Q underflow is coming here, Q is going out, this is the supernatant which is relatively clear, and here I have the Q underflow, right, and here the concentration is Cn, and here the concentration is relatively higher Cu, let us see, right. So, that is something to keep in mind, and here it is relatively clearer or lesser concentration. So, first Q plus Qu into Cn, the mass of solids coming in, is more or less or approximately equal to Qu into Cu. We are assuming that most of it is coming down in this underflow, let us say, right. So, Qu into Cu, and that is going to be equal to the total flux, right, total flux into the cross sectional area. That is something to keep in mind, and this is what at steady state. As you know, Q in is equal to Q plus Qu, Q in, and A is the area of the tank. That is something to understand. So, the cross sectional area A is Q in C in, right, Q in C in is Q plus Qu into Cn by GL. This is what I mentioned earlier in the design, the loading rate by the limiting flux, then you will get the cross sectional area, right. This is what we discussed earlier too, if you remember. So, this is the minimum surface area of the tank, that is what do we say required, assuming that we are running the plant properly at steady state flux that is equal to G limiting, right. That is something to keep in mind. So, flux applied is equal to the flux transferred to underflow, that is the ideal case, this is the ideal case, right. So, the flux that is coming in, right, Q in C in will be equal to Qu Cu, let us see, right. So, that is we are talking about the solids here, most of the solids we are assuming are being removed from here, right. It is not what do we say, we are assuming that relatively little is going out. So, that is something to keep in mind, right. Okay. So, let us look at that. Okay. But if the flux applied is greater than the flux transferred to the underflow, right, if the total underflow one is relatively what do we say lesser than the flux that is coming into the tank, then what is going to happen? Obviously, solids will accumulate in the system. Earlier if my zone is somewhere here, maybe now depending upon how much more I am putting in, the zone which was here or the interface will be here, and if I keep adding much more, it is going to go somewhere out here, and then you can have overflow, right. The sludge blanket volume will increase and sludge blanket height. So, this is the sludge blanket height, it will also rise. If the flux applied is less than the flux being removed through the underflow or to the underflow, then what is going to happen? So, here the sludge blanket depth will decrease, right, and then solids will leave the settler, right. Solids will leave the settler, eventually eliminating the sludge blanket, right, and that is something also that you do not want to have, right, eventually eliminating the sludge blanket. So, that is something to keep in mind. So, we want to see to it that the flux applied is more or less near or such equal to that flux from calculated from that G limiting, let us say, right. So, that is something to keep in mind. So, gravity sludge thickening, let us look at what we have. So, what are the operating criterion? Solid applied per unit bottom area, right. How much solid am I applying per unit bottom area, that is something to keep in mind. And typically looks like for primary it is 150 kgs per meter square per day, and for primary it is relatively lower, yes, and for AST it is much lower. Obviously, it depends upon how easily the relevant particles can be separated or the velocity of that particular zone settling, I guess, right. So, that is something to keep in mind, and as I mentioned, the bottom sludge blanket, it should be 1 meter deep, let us see, right, ideal one. For good sludge compaction, we want a retention time to be around 24 hours, let us say, typical 24 hours. So, this is what we see out here. So, I am feeding it here, yes, and you can see the relevant pickets. I think this is the top view, right, and it is rotating in this manner, right, and slowly but surely you are going to have the supernatant leaving from these troughs which are at the periphery, let us see, right. So, let us look at this. So, these are the pickets. Again, we are not going to have mixing that is going to shear the flocks or such, you are just going to have gentle mixing, so that you are going to have some concentration of the relevant solids, right, that is something to keep in mind. So, here you are going to have the thickened sludge removed, this was the underflow, let us see, right. So, that is something to keep in mind. So, feed sludge coming in, and then you are going to have the sludge blanket somewhere here or such, yes, and then the underflow out here, and the supernatant obviously where, and then the supernatant it is going to be removed in this way, right. So, that is something to keep in mind. Another one is the gravity belt thickener. So, here the principle is that typically used for water treatment plant primary sludge, you have a belt, again keep in mind that here it is still gravity, and on the belt let us say you are going to have different rakes or such. So, as the sludge moves in, these rakes they are going to part or cleave the relevant sludge, yes, and then you are going to have a relatively permeable belt, and by gravity the water is going to be collected at the bottom. So, there is one more aspect, let us look at that when we see the figure, right, gravity belt thickener. So, what do we have? Sludge is applied to a fabric belt which will allow the water to flow through it. Water drains through the belt as I just mentioned, and sludge is turned over by blades. Depending upon the type of sludge, polymer coagulation will be needed. So, let us see what we have. Here I am adding the polymer, right, and here is the flocculation tank, I am going to have the flocculation, and then as this particular sludge moves here, let us say I am going to have plows or sometimes rakes that will cleave the relevant sludge. In the meantime, the water is going to filter through this fabric, this is my fabric, let us say, right. Sometimes you will have more layers as you can see here, sometimes not, let us say, yes, and so this sludge after it comes here, it is going to back up here and it is going to fall back here, right. The sludge is moving in this direction gently and it is going to fall back here. So, again here you are going to have more retention time and also more dewatering at this stage. So, that is one aspect to keep in mind, that is why they have this adjustable ramp here depending upon the time they want the sludge to spend here, right. So, that is something to keep in mind. And what else? Gravity belt thickener, obviously it is about hydraulic loading, right, and looks like that is around 800 liters per meter per minute, let us say, right, 800 liters per minute, pardon me, per meter per minute, and solids loading is around 200 to 600 kgs per meter per hour. Again, general values, you do not need to mug these up for the exam or such or even for the homework, these are general values that we wanted to mention there. Here one is hydraulics loading with respect to water, and here with respect to solids, let us say, right. So, that is why we are multiplying it with the concentration, that is something to keep in mind. So, dissolved air flotation, As I mentioned, especially in the context of what do we say, secondary settling tank sludge, where the flocks are relatively more buoyant, right, and you have water entrapped in the flocks and such. So, that is when you will typically look at dissolved air flotation. Let us look at what we have. We already discussed this, so I am going to move on. So, saturated water with air at relatively higher pressure is going to be pumped in, and you are going to release saturation. And what is it that we are trying to do? We are going to form bubbles, and they are going to attach to the solids, and these solids are now going to be moving up. So, this is the reverse of the gravity settling or thickener that we looked at earlier, let us see, right. So, let us see, there are two ways or two modes of dissolved air flotation. One is without recycle and the other one is with recycle. So, we will look at the figure for with recycle soon. So, without recycle, the mechanism, air bubbles form and they will take the relevant solids onto the solid surface, and solid and that bubble part is going to be less dense than water, that is why it is going to move up, right. So, this rise velocity is similar to the settling velocity, as I mentioned, it is upside down or similar to the upside down sedimentation tank, let us see, right. So, applications, where is it? Typically for light solids or oily sludge, right. So, as I mentioned. So, with recycle, same mechanism as without recycle, but what are the advantages? We will look at the figure. Solids do not go through the pressure release valve, as in, let me look at the figure and then we will come back to these advantages. So, here we see that, okay, we have the pressure reducer or pressure release valve, we are going to have the pump which is going to pump the air, and here we have the air dissolution tank, air is being dissolved, it is mixing with the influent and then it is coming in here, right. And as you see, some of the effluent is being recycled. So, in the earlier case though, that would not have been it, the water or the air would be directly spent up here. So, that is why there are some disadvantages in the system without the recycle. So, let us look at and see what are the advantages with this recycle flow. As you can see, the recycle flow, you are pumping the air into that recycle flow, right, and then that is coming in contact with the influent, and here you have the relevant lighter particles being formed because of the air bubbles and the solids on the air bubbles, and these solids being lighter than water, less dense, are going to be collected up, and you have a float collector where the sludge is being taken out or collected, let us say, that is the relevant aspect. So, now let us look at the advantages. So, solids do not go through the pressure release valve. So, why is that an advantage? Because of that there are no turbulent conditions. Why is that again important? Because then the flocks are not sheared, let us say, right. So, this is the relevant aspect, flocks are not sheared. Again, if flocks are sheared, again you are going to have issues with respect to thickening. So, the flocks are not sheared, let us see, right. So, that is not thickening with respect to separation and being taken up, right. And obviously, we can control the air to solid ratio by controlling the rate of recycle flow, as in by the rate at which you can recycle it, you can control the air to solid ratio, which is analogous to what do we say, controlling the amount of what do we say, discharge or the sludge that is going to be collected at the top. So, design aspect, typically we look at air to solid ratio, right, and then we are going to correlate this ratio with the rise velocity and the design thickener as with solid flux method. Earlier with respect to the solid flux method, in the gravity thickener we looked at it. So, in the similar manner, here we are going to look at the air solids ratio and look at it in conjunction with rise velocity, let us say, right. So, that is something to keep in mind. Yes, let us move on. So, design requirements, typical air to solid ratio, as you can see, is not very high, but significant enough, 2 to 4%, and hydraulic loading rate, right. And one aspect to note is that typically because of the mode of operation, the area required for dissolved air flotation devices is going to be relatively lesser than the one that is required for your gravity thickener. That is something to keep in mind. But again, the kind of sludge that the gravity thickener can deal with and the kind of sludge that the dissolved air flotation can deal with are relatively different. So, obviously, some people mix it, but again note that lighter sludge relatively better with dissolved air flotation, right. So, in the next session we will move on to stabilization. Until now we looked at increasing the solids concentration, removing as much water as we can, right, or increasing the concentration of the solids in my particular sludge. That is what we have done. In the next step we are going to look at decreasing the organic concentration or the biodegradability of the relevant sludge, right. With that, I will end today's session.